Why do you think Einstein didn't believe his own equations and didn't think that black holes are real? Why was that such a difficult idea for him?
Well, something very interesting happens in Schwarzschild's solution of the Einstein equation. I think his reasoning was ultimately wrong, but let me explain to you what it was. At the center of the black hole, behind the horizon, in a region that nobody can see and live to tell about it, at the center of the black hole, there's a singularity, and if you pass the horizon, you go into the singularity, you get crushed, and that's the end of everything. Now, the word singularity means that it just means that Einstein's equations break down. They become infinite. You write them down, you put them on the computer. When the computer hits that singularity, it crashes. Everything becomes infinite. There's two. So the equations are just no good there.
Mm-hmm.
Now, that's actually not a bad thing. It's a really good thing. And let me explain why. So it's an odd thing that Maxwell's theory and Newton's theory never exhibit this phenomena. You write them down, you can solve them exactly. They're really Newton's theory of gravity. They're really very simple theories. You can solve them. Well, you can't solve the three-body problem, but you can certainly solve a lot of things about them. Nevertheless, there was never any reason, even though Maxwell and Newton perhaps fell for this trap, there were never any reason to think that these equations were exact. And there's no equation. Well, there's some equations that we've written down that we still think are exact. Some people still think are exact. My view is that there's no exact equation.
Everything is an approximation.
Everything is an approximation.
And you're trying to get as close as possible.
Yeah.
So you're saying objective truth doesn't exist in this world? The internet's going to be very mad at you.
We could discuss that, but that's a different thing. We wouldn't say Newton's theory was wrong. It had very, very small corrections, incredibly small corrections. It's actually a puzzle why they're so small. So if you watch the precession of Mercury's perihelion, this was the first indication of something going wrong. According to Newton's theory, Mercury has an elliptical orbit. The long part of it moves around as other planets come by and perturb it and so on. And so this was measured by Leverrier in 1859, and he compared theory and experiment, and he found out that the perihelion precess moves around the sun once every 233 centuries instead of every 231 centuries. Okay, now, this is the wonderful thing about science. Why was this guy? I mean, you don't have any idea how much work this is, But, of course, he made one of the greatest discoveries in the history of science without, even knowing what good it was going to be.
Mm-hmm.
So that's how small, that was the first sign that there was something wrong with Newton.
Yeah.
Now, so the corrections to Newton's law are very, very small, but they're definitely there. The corrections to electromagnetism, they're mostly, the ones that we see are mostly coming from quantum effects. And
so the corrections there for Maxwell's equations is when you get super tiny, and then the corrections for the for Newton's laws of gravity is when you get super big. That's when you require corrections.
That's true, but I would phrase it as saying when it's super accurate. If you look at the Bohr atom, Maxwell electromagnetism is not a very good approximation to the force between the proton and the electron. The quantum mechanics, if you didn't have quantum mechanics, the electron would spiral into the proton and the atom would collapse. It's quantum, so that's a huge correction there.
Sure.
So every theory gets corrected as we learn more. There'd just be no reason to suppose that it should be otherwise.
How does this relate to the singularity? Why the singularity is
So
uncomfortable?
when you hit the singularity, you know that you need some improvement to Einstein's theory of gravity. And that improvement, we understand what kind of things that improvement should involve.
Mm-hmm.
It should involve quantum mechanics. Quantum effects become important there. It's a small thing. And we don't understand exactly what the theory is, but we know there's no reason to think, Einstein's theory was invented to describe weakly curved things, the solar system, and so on. It's incredibly robust that we now see that it works very well near the horizons of around black holes and so on. So it's a good thing that the theory drives itself, that it predicts its own demise. Newton's gravity had its demise. There were regimes in which it wasn't valid.
Mm-hmm.
Maxwell's electromagnetism had its demise. There was regimes in which quantum effects greatly modified the equations. But general relativity, all on its own, drove a system which originally was fine, would perversely wander off into a configuration in which Einstein's equations no longer applied.
So to you, the edges of the theory are wonderful. The failures of the
edges are wonderful because that keeps us in business.
So one of the things you said, I think, in your TED talk, that the fact that quantum mechanics and relativity don't describe everything, and then they clash, is wonderful. I forget the adjective you used, but it was something like this. So why is that? Why is that interesting to you? In that same way that there's contradictions that create discovery?
There's no question in my mind. Yeah. Of course, many people would disagree with me, that now is the most wonderful time to be a physicist.
Why is that?
So people look back at it's a classical thing to say among physicists, I wish it were 1920.
Right.
Quantum mechanics had been just understood. There was the periodic table. But in fact, that was such a rich thing that a lot of exciting stuff happened around 1920. It took a whole century to sort out the new insights that we got,
especially adding some experimental stuff into the bunch, actually making observations and integrating all the
experimental thing.
All the computers also help with visualizations and all that kind of stuff.
Yeah. It was a whole sort of wonderful century. I mean, the seed of general relativity was the incompatibility of Maxwell's theory of the electromagnetic field with Newton's laws of gravity. They were incompatible because if you look at Maxwell's theory, there's a contradiction if anything goes faster than the speed of light. But Newton's theory of gravity, the gravitational field, the gravitational force, is instantaneously transmitted across the entire universe. So you could, if you had a a friend on, in another galaxy with a very sensitive measuring device that could measure the gravitational field. They could just take this cup of coffee and move it up and down and Morse code, and they could get the message instantaneously over another galaxy. That leads to all kinds of contradictions. It's not self-consistent. It was exactly in resolving those contradictions that Einstein came up with the general theory of relativity. And it's fascinating how this contradiction, which seems like maybe it's kind of technical thing, led to a whole new vision of the universe. Now, let's not get fooled, because lots of contradictions are technical things. We haven't set up we run into other kinds of contradictions that are technical, and they don't seem to, we understood something wrong, we made a mistake, we set up our equations in the wrong way, we didn't translate the formalisms.
As opposed to revealing some deep mystery that's yet to be uncovered.
Yeah. And so we're never very sure which are the really important ones.
But to you, the difference between quantum mechanics and general relativity the tension, the contradiction there seems to hint at some deeper thing that's going to be discovered in the century.
Yes, because that one has been understood since the 50s. Pauli was the first person to notice it, and Hawking in the early 70s gave it a really much more visceral form. And people have been hurling themselves at it, trying to reduce it to some technicality, but nobody has succeeded. And the efforts to understand it have led to all kinds of interesting relations between quantum systems and applications to other fields and so on.